Hello everyone. In this video, we will discuss about per unit system for transformer. We are going to deal with single phase and three phase transformer. Okay. So we know that what is per unit system? What is the purpose for the per unit system? So normally per unit systems are deal with power system calculations. So when we do the power system calculations, per unit system simplify that calculation. Yeah. So for example, if you consider the transformer, in the transformer we have a two side. One is primary side and second one is secondary side. So in the primary side impedance and secondary side impedance are different. So when we do the calculation, when we do the power system calculation with actual value, we have a problem to calculate the transformer impedance because we have a two side of impedance. But when we deal with the power per unit system, we can simplify those calculations. Okay, normally first we will define the per unit system. We know per unit is equal to actual value is divided by base value. Per unit is equal to actual value divided by base value. So this is the equation for per unit. Okay, we will discuss about base value. Normally, when we do the power system calculations or when we convert to per unit, we have to define the base value. Yeah, we have to define base value. Normally, two base values are defined with respect to the power system devices. For example, in power system generator, for example, if we consider the power system, in the generator rated voltage, generator rated power are used for base value. So when we deal with the base value, we are defining two base values. One is voltage, another one is power. We define these two base values with respect to power system generator or transformer. Anyway, after defining these two base values, we can define another values. For example, current or impedance. Normally, when we define the power, we can use apparent power. Or sometimes we can use real or reactive power. Okay, so usually we are using apparent power for base value of the power. Anyway, from these two base values, voltage base value and power base value, from these two base values we can define another two base values. One is current. So we know that our usual electrics equation, I is equal to power divided by voltage. Yeah. So the base current is equal to power, apparent power. I am defining S using a S, and voltage V base. So I base current is equal to base power, apparent power and base voltage. From these two we can calculate the base current. At the same time we can define impedance. We know the impedance is equal to V square by S. Yeah, V square by S. How can we get this equation? So you can remember. So we know power is equal to VI. So here we can define that V square V by impedance. From that, impedance is equal to V square by S. So the base impedance is equal to base voltage square by base power. So this is the base impedance equation, this is the base current equation, and these two, voltage and power, are defined with respect to the power system, for example generator or transformer. So when we define the voltage and power in the power system, we have to select the value from the generator or transformer. It should be a rated value or maximum value. So when you select the voltage and power base value, we can use rated value or maximum value. Okay. Now we will discuss about the power per unit conversion. Now we will discuss about per unit conversion. Okay. Okay. Now we will discuss about per unit conversion from one base to another base. So first, why we have to convert per unit from one base to another base? What is the purpose? Why we have to convert from one base to another base? Because when we deal with the power system, we have a lot of transformers. For example, here I consider two transformers, two different transformers. Okay, these two transformers are defined with two different base value. So this transformer defined with S1 base value, apparent power, and this transformer apparent power is S2 base value. Okay, so we know that this transformer per unit value, which is mentioned in the nameplate of the transformer, this transformer per unit is defined with S1 base value. This transformer per unit is defined with S2 base value. So when we deal with the per unit system, we should have a single base values for apparent power, for voltage. Okay, so we should have a single base value. But in this system, we have two different base value, and we have a two different, according to that base value, we have a different per unit system. So we have to convert this base value to another base value. For example, I am going to convert this base value to another base value. For example, S1 base value. So this transformer defined with S2 base value. Now I am going to define the per unit with S1 base value. Okay. So S2 base value defined per unit is old one. S1 base defined per unit is new one. Okay. So this is the old per unit which is defined in this transformer nameplate. Now we have to convert to S1 base value. So this is called new per unit. So the per unit value, the old per unit is equal to this transformer actual power is divided by this transformer base value. So what is the old base value? S2 base value. Now we will convert per unit for S1 according to the S1 base. So which is S1 here. Okay. So per unit, new per unit is equal to S actual is divided by S1 base value. Okay. So this is the new per unit. This is the old per unit. So old per unit is defined with S2. New per unit defined with S1. Now we will divide these two equations. 1, 2. 1, 2. So per unit new is divided by per unit old is equal to this equation is divided by this equation. So from that we can say S1 base, okay, S1 base, S2 base value. Yeah, if you divide these two equations, you will get this type of equations. From that, per unit new value, per unit new is equal to per unit old multiplied by S2 base divided by S1 base. S2 mean old base value. S1 mean new base value. Okay. So this is the new per unit of this transformer. So if you convert this transformer for new per unit, now we have this true transformer with S1 base value. So we have defined with the single base value. So have you got the idea for per unit system conversion for apparent power? Now we will discuss about the voltage and impedance conversion. Okay. Okay, so we know per unit new value for apparent power is equal to old value for per unit apparent power is multiplied by the old base value and new base value. Okay, now we can use this equation for voltage and current also. So for example, the voltage per unit, the voltage new per unit is equal to similar equation, voltage per unit old multiplied by old base divided with voltage new base. Okay, so this is the equation for voltage. Similar equation we can use for current also. So current per unit new per unit is equal to current per old per unit multiply with current old base divided with current new base. Okay, so these are the equations for per unit conversion for apparent power, voltage and current. Now we will deal with the impedance, per unit impedance conversion. Okay, so we will discuss about that. So we know that the impedance per unit is equal to impedance actual value is divided with base value. Yeah, base value. From that we already convert this equation to according to the voltage and power. We know that Z actual value is divided with base value. Base value is equal to voltage base square divided with S base. It is multiplied with here S base. Yeah, you can remember Z base is equal to V base square divided by S base. So if you substitute this value, we can get this type of equation. Okay, now we will define new per unit. So per unit, new per unit is equal to actual impedance and new base value and new base voltage, new base power, new base voltage. Okay, and old per unit is equal to actual value. Actual value is doesn't change. Okay, so actual value multiply by old apparent power, old base power. Okay, old voltage. So per unit old one, per unit new one. So now we will we will divide these two equations. So per unit new 2 divided by 1, per unit new, per unit old is equal to z actual cancel out. So s base new, okay, here s base old, v base square new, here v base old, okay. So from that we can say new per unit impedance new per unit is equal to old per unit multiply by new base power, old base power, new old base voltage square divided with new base voltage square. Base old and base new. So this is the new per unit impedance for impedance. Okay. So these are the equations for per unit conversion. Now we will discuss about the three-phase system. We will discuss about per unit with three-phase system. Okay. Okay. Now we will discuss about per unit system for three-phase transformer or three-phase power system. Okay. We know that if you consider that three-phase transformer power is defined, apparent power is defined with respect to three-phase. But when we deal with the per unit system, we have to find out the base value for single phase. Okay, we have to find out the base value for single phase. So for example, three-phase transformer apparent power is defined as three-phase base value. So this is the three-phase transformer apparent power. Okay. Now we have to calculate the single-phase base value. Single-phase base value. So what is the single-phase base value from this three-phase base value? Very simple, yeah. Three-phase base value is divided by 3. We can get single-phase base value. Okay. So same idea we can apply for voltage. So phase voltage, that means single phase phase voltage. So the phase voltage is equal to line to line voltage divided by root of 3. So this equation valid for this equation valid for Y or star connection. So phase base voltage is equal to line to line voltage divided by root of 3, and we can define the current. We know the current is equal to base current is equal to base power divided by base voltage. Therefore base power, we know that single base power is equal to 3-phase base power divided by 3, and single phase base voltage, we know if you consider the Y connection, single phase base voltage is equal to line to line base voltage divided by root of 3. From that the base current is equal to 3-phase base divided by root of 3 line to line base voltage. So this is okay. So base current is equal to 3-phase base apparent power divided by root of 3 line to line base voltage. Okay. Now we will deal with the impedance. So impedance is equal to base impedance is equal to base voltage. We know that base voltage square divided by base power. So pace base volt, single pace base voltage, single pace, so pace base power. So from that we know pace, single pace base voltage square, single pace base apparent power is equal to 3 pace base power divided with 3. So from that we can say the base impedance is equal to 3 pace base voltage square divided by 3 pace base power. Okay, so this is the equation for impedance value, base impedance value. So these are the equations we are going to deal with the 3-phase per unit system. Okay, now we will discuss about transformer voltage regulation and efficiency. So first, to get the idea about voltage regulation, we have to remember the transformer equivalent circuit. We know that the transformer has a two sides, one is primary and secondary. So the primary secondary winding has a losses, it represents with this impedance. So in the primary side you can see here RP primary resistance and primary side inductance. The same idea for in the secondary side, so secondary resistance and secondary reactance. Okay, at the same time in the transformer it has a core losses, eddy current losses, hysteresis losses. So these core losses represent with this admittance, this excitant branch. This is called excitation branch. Okay, so this is the core resistance and inductance part, reactance part. Anyway, now we can convert this transformer equivalent circuit to refer with primary side. If you consider this transformer equivalent circuit with primary side, we can define Vp and secondary voltage Vs defined with A into Vs. What is A? What is A? We know A is the turn ratio. A is turn ratio of the transformer. Anyway, so if you refer with the primary side, we can draw this equivalent circuit. Here there is no changes in the primary side impedance. So when we refer with the primary side, the secondary impedance are multiplied by A square. So A square Rs, A square XS. Okay. At the same time, the current. So we know this is the secondary current Is. So if you refer with the primary, the secondary current divided by Is, A divided by A, Is by A. Okay. So this is the primary, refer with the primary equivalent circuit. Second one, refer with the transformer equivalent circuit or refer with secondary side or low voltage side. So when we consider that part, we know the secondary voltage is Vs. At the same time, the input voltage is Vp by A. Vp by A. Okay, and there is no changes in the secondary impedance. But if you consider the primary impedance are divided by A square. Rp by A square, Jxp by A square. At the same time, if you consider the current, secondary current is called Is. At the same time, the primary side input current is called AIP. So this is the transformer equivalent circuit for refer with secondary. This is the transformer equivalent circuit refer with the primary or high voltage side. Okay. Now we can improve this transformer equivalent circuit. For example, if you neglect the excitation branch, okay, so that's mean if you neglect this part, so we can refer this secondary Vp by A, Vs. If you neglect this excitation branch, we can rearrange this equivalent circuit Rp by A square, Jxp A square, RS JXS. Okay, so refer with secondary side. So we neglect the excitation branch. Now why we are going to why can we neglect this excitation branch? Normally this excitation current normally if you consider the transformer, this excitation current with a full load just 3 to 5 percentage. So the excitation current is very small. Because of that we can neglect this part. So if we neglect excitation branch, we can get this kind of equivalent circuit, and we can rearrange this equivalent circuit. We know these two are resistance, so we can say equivalent resistance, and these two are reactance, so we can draw equivalent reactance. Okay, so this is primary side, input side, and this is output side. Refer with secondary. So R equivalent is equal to Rp by A square plus Rs. Jx equivalent is equal to Jxp A square plus Jxs. So this is the transformer equivalent circuit with neglect the excitation branch. Okay. Now we will discuss about voltage regulation. So now in the transformer windings have impedance. Transformer winding has impedance. So we are defining equivalent impedance. We are defining equivalent impedance. So when you connect the load in the transformer, the current draws through this transformer. Okay. Therefore, because of this impedance, there will be a voltage drop. Okay. This current is varying with respect to this load value. Then the secondary voltage in the transformer, secondary voltage also varying with this load value. So if you change the load value, then the current will change. So the current is changing, then the voltage drop is also changed. Because of that, the secondary voltage is varying with respect to this load value. Okay. Here, even if you keep constant the input voltage, the secondary voltage is varying with respect to load value. Therefore, we are going to define voltage regulation. Voltage regulation measure a change in secondary voltage. Voltage regulation is measure a change in secondary voltage from no load to full load. Expressed with full load voltage. So voltage regulation means the change in secondary voltage from no load to full load. Therefore, voltage regulation is equal to secondary voltage, no load secondary voltage minus secondary full load voltage expressed with secondary full load voltage, and it is expressed with percentage also. So multiply by 100. So this is the voltage regulation equation. Okay, have you got the idea? So normally why we are defining voltage regulation? Simply we can say in the transformer load is varying. So if you change the load of the transformer, then the secondary voltage also varying with respect to that voltage. Therefore, we are defining voltage regulation. Okay. Now we are going to modify this voltage regulation equation. We know this is the secondary voltage in no load condition. And this is the secondary voltage in full load condition. Okay. So full load condition means the transformer maximum limited current flowing at that full load condition. Okay. Anyway, now we will define secondary voltage in no load condition. So if you consider no load, there is any load here. Okay. At that time, if you consider no load condition, at that time there is no current flowing through this transformer. Yeah. So we don't have any load here. Because of that, there is no current flowing through this winding or this transformer. So we can neglect excitation current. Okay. Anyway, so the current flowing through this transformer or this winding is 0. Because of that, the voltage drop also 0. Then we can say the secondary voltage, this Vs, is equal to Vp by A. Yeah, the secondary voltage, there is no voltage drop, so we can say the secondary voltage is equal to Vp by A. So the voltage here is 0. So both are equal. So voltage regulation is equal to no load condition, we can say Vp by A. So at no load condition, Vs is equal to Vp by A. Both are equal. Minus secondary full load divided by secondary full load condition. Okay. And we can define this voltage regulation with respect to per unit system. We can define this voltage regulation with respect to per unit system. So if you consider per unit system, so secondary no load condition voltage. We know secondary no load condition voltage is equal to Vp by A. So we can say primary per unit. Yeah. And secondary full load condition, we can say secondary per unit and full load condition is divided by secondary per unit and full load condition. Okay, full load condition multiplied by 100. So this is the voltage regulation per unit with respect to the per unit system. Okay. So these are the equations we define in voltage regulation. Now we will discuss about how voltage regulation varying with load. For example, if you consider the transformer load side has a leading power factor, or the transformer has a lagging power factor, or transformer has a unity power factor. With respect to this different type of voltage, we are going to define the voltage regulation. Okay. Okay. Now first we will define the equation for this transformer. Okay. Here we can write the equation Vp by A. Vp by A is equal to Vs plus there is a voltage drop here, so Vs plus Is into R equivalent plus Jx equivalent. So Vp by A is equal to Vs plus Is R equivalent plus Jx equivalent. Now from this equation we are going to deal with the different type of load or different type of power factor. First we will deal with lagging power factor. So, lagging power factor, okay. So in the transformer in the lagging power factor, at that time we are going to draw the phasor diagram for this voltage. So Vs, this is Vs, and the current draw through this transformer. This current draw through this transformer has a lagging. Because of that, I am drawing a current here, Is. So Vs plus Is into R equivalent. Yeah, Is into R equivalent. So Is in this line, therefore Is into R equivalent should be parallel with this Is. So Is into R equivalent here. Then Is into Jx equivalent. So there is a Is into Jx equivalent. Because of that, so there will be a perpendicular value, perpendicular, because Is into Jx equivalent. So this is J Is x equivalent. Okay, so this should be perpendicular to this Is value. Yeah. So we can say Vs plus Is R equivalent plus Is x equivalent. So if you add these three, you will get Vp by A. So this is Vp by A. Okay. This is Vp by A. From this phasor diagram, we can see this Vp by A value is larger than Vs value. Yeah, Vp by A is greater than Vs value. Therefore, the voltage regulation for lagging power factor, is greater than 0. Greater than 0. You got the idea? Lagging power factor, voltage regulation greater than 0 because Vp by A is greater than Vs. Okay. So this is the first case. Second, we are going to deal with the transformer in unity power factor. Unity power factor. So if you consider the transformer unity power factor, first we will define Vs. Then we know there is a unity power factor. There is no phase difference with voltage and current. So the Is should be in same phase, in phase. Okay. Therefore, Is into R equivalent should be here. Yeah, this is Is into R equivalent. So Vs plus Is into R equivalent. Then Jis x equivalent should be perpendicular to this Is into R equivalent. So this is Jis x equivalent. So Vs plus Is R equivalent plus Jis x equivalent. This should be equal to Vp by A. So this is Vp by A. Here also we can say the Vp by A is greater than this Vs. Vp by A is greater than Vs. So we can write here Vp by A is greater than Vs. Then we can say voltage regulation is greater than 0. Voltage regulation is greater than 0 for transformer unity power factor. Okay. Okay. Now we will deal with leading power factor. Leading power factor. So in the transformer in leading power factor, Okay, so first we will draw the phasor diagram. Vs, and so the current is leading. Yeah, current is leading power factor Is. Because of that, Is into R equivalent should be like this. Is into R equivalent, and Is into Jx equivalent should be perpendicular to this here. J Is x equivalent. Therefore, Vs plus Is R equivalent plus J Is x equivalent should be Vp by A. Okay. So when we use the transformer in leading power factor, okay, so it means capacitive load. Okay, so lagging power factor means there will be a inductive load. Leading power factor means there will be a capacitive load. So in the leading power factor, the voltage regulation, usual transformer, the leading power factor voltage regulation would be negative. Voltage regulation would be negative, less than 0. Okay. So we know in the transformer, leading power factor and unity power factor voltage regulation are greater than 0, and leading power factor voltage regulation less than 0. From that we can say there is no voltage regulation in 0. Okay, so there is no zero voltage regulation. So only for ideal transformer. If you consider an ideal transformer, then there will be a zero voltage regulation. In practically, there is no zero voltage regulation. Zero voltage regulation means Vs and Vp by AR should be equal. Yeah. Zero voltage regulation means Vp by A, and it means full load voltage and no load voltage are both are equal. That is zero voltage regulation. But in practically there is no zero voltage regulation. At the same time, the voltage regulation is greater than 0, then the secondary side voltage, is decreasing. Yeah, because of this voltage drop. At the same time, the voltage regulation of the transformer is minus or less than 0, then the secondary voltage is rising. Yeah, secondary voltage is rising because of that capacitive load. We are saying leading power factor means the load is capacitive. Because of that, the secondary voltage is rising. Okay, so normally in the lagging power factor, voltage is decreasing. In the leading power factor, secondary voltage is increasing. Okay, anyway, so I think you have got a clear idea about leading, lagging and zero voltage regulations. Okay, now we will define about transformer efficiency. So transformer efficiency is equal to output power divided by input power multiplied by 100. So normally these are the real powers. Okay, output real power, input real power multiplied by 100. So from that we can define this power P out. So what is input power? Input power is equal to output power plus transformer losses. What are the losses occur in the transformer? One is core losses and second one is copper losses. Core losses are divided by two. One is hysteresis loss and eddy current loss. Anyway, the input power is equal to output power plus power loss. Yeah. From that, output power divided by output power plus loss. Loss mean copper loss plus core loss. Copper loss plus core loss. So this is the transformer efficiency. From this we can define the output power. We can define the output power. So what is output power? We know output voltage, secondary voltage Vs, secondary current Is. If you consider power factor cos theta, then output power we know Vs, Is, cos theta, output power. And the input power, Vs, Is, cos theta plus copper loss and core loss. Okay, so this is the transformer efficiency equation. Okay, I hope you have got the basic idea about the transformer efficiency, voltage regulation per unit system. Now we will deal with the examples. We are going to discuss some different type of examples. Okay,